Good morning, everyone. I'm Sonal Thingne. I'm a postdoctoral associate at Department of Mechanical Engineering in MIT. And today I'm going to talk about optimizing startup and shutdown phases for continuous biomass reactors. Most of the work that we see reported on continuous biomass reactors like gasifiers, pyrolyzers, torrefactors are on the steady state or the normal operation of the reactor. And very few attention has been given to startup and shutdown procedures through the research perspective. So these are like typical biomass reactors which I'm going to focus on, mainly the biomass torrefaction one, because these are the reactors which we work on at MIT in our lab at Reacting Gas Dynamics Laboratory. We have these torrefactions of equipment of different scales, like 1 kg per hour to 10 kg per hour. I won't go into details of the process of torrefaction, as like before, the talk before me was on pyrolysis. And torrefaction is a kind of mild pyrolysis which takes place in the temperature range of 200 to 300 degrees Celsius in inert atmosphere or in slight oxidative environment. So our earlier work was focused on reaction kinetics, proposing mechanism for torrefaction, then reactor design, mathematical modeling at particle levels and reactor scales, and the experimental parametric analysis for different biomass feedstock. And we could produce a range of biochars at different operating conditions from both of these reactors. So today I would be talking about how do we characterize the startup and shutdown for these reactors. And in a more or less, the procedure to start up these continuous reactors is similar, and that's why I kept my title quite generic. Like, it can be applied to gasifier as well as pyrolyzer operating in continuous operation. The only difference would be the temperatures required would be higher, so we would burn some more biomass or we would have to provide some more heat. So the motivation for this study came out from like my colleague, like Kevin. He has set up a company which is taking torrefaction technology to market. And what we found, like startup and shutdown are one of the prior like issues of concern for plant operators, because for biomass-based plants, it takes usually longer time to achieve the steady state operation. And this achieving steady state is important to get a consistent quality of torrefied product. Also, like if you look at safety incidents, they happen mostly during startup and shutdown and not during the normal procedure of the reactor as per Chemical Process Safety Center. And as I said, like we have to look at it from the research perspective. And there are a few reports and studies on batch scale reactors for gasifiers especially, but for continuous thermochemical reactors, it's little lacking. So it's a thermochemical reactor, so we need heat, and there are common approaches for providing heat. Either we can provide it for electric or jacketed heating using thermal fluid, using burning fossil fuel like coal, oil, or gas, and using portion of raw biomass as a feedstock in the reactor, if we are doing it in oxidative medium and not completely inert medium. But the first two, like actually for lab scale reactor, it doesn't matter how do we heat up the reactor. But at commercial scale, it does matter, like because we want to attain that steady state quickly for our operation to start. So, but we don't want to lose on this renewable and carbon neutrality nature of biomass, so I would focus mainly on using the portion of raw feedstock within the reactor itself to, like, for the startup phase. So there are several factors affecting the startup and shutdown time scales of reactor, like air, biomass, their ratios, reactor dimensions, insulation, and then all sorts of like gas solid mixing and heat and mass transfer aspects. And when I said like we are looking at decentralized applications of torrefaction, different users may have different priorities over how do they operate reactor and how do they reach the steady state condition. So these priorities can be something like this, like in startup, someone who's working on expensive or a scarce biomass, his main objective would be minimizing the amount of biomass getting consumed in the startup phase. He can like ensure like, okay, he can go for longer time, but he should minimize biomass. Similarly, for someone who is having cheap or plenty biomass available, for them, the main objective function would be like minimizing total startup time. Doesn't matter if he spends more biomass for the startup. And for shutdown, similarly, based on the condition, it may be a priority to minimize the time for cooling the reactor or maximize the time for cooling the reactor. Suppose in decentralized application, if a torrefaction unit has to be transported from one site to another site nearby, we don't want to start from scratch all over again. So if we could maximize the reactor cooling time, we can just start at the next site for the operation. And for minimizing time, if an operator wants to leave early, he wants to make sure he cools the reactor quickly. Or if a reactor malfunctions and need to be fixed for a quick repair, we should have a strategy to minimize the time taken for cooling the reactor. So based on these priorities and the earlier concepts I explained, for a same reactor, there may be different strategies that might have to be adopted for starting or shutting down the reactor. And this brings us to the objective of the present work. Like, we want to provide a conceptual framework to canalize and understand these startup and shutdown phases of the reactor. So we did some experiments on the lab scale reactor, which I showed earlier for 1 kg per hour, and we are like doing some more experiments on the scaled up prototype. And we have developed a model, like simple conceptual models based on heat transfer mechanisms, and predicted them for the scaled up versions of reactor. So today I will be focusing mainly on starting from cold state and the quick shutdown of the reactor. We also have the data for the transitioning between two operating conditions as well as slow cooling down, but in the course of time I'll just cover first two. So for the first one, like starting reactor from cold state, we need power for heating the reactor. So we need a measure. How do we give it a measurable quantity? So we call it as biomass mass flux, because that would be like a fixed quantity for any scale of reactor. And the strategy is like initially we burn biomass at a stoichiometric combustion ratio, like little higher than that, so to ensure complete burning of biomass and attaining the highest possible temperature to minimize that startup time. So these are the experimental results for a flux of say 4 gram per second meter square for 1 kg per hour reactor. Because it was very thick, the reactor wall like 6.4 mm, so we took like almost 150-60 minutes to, that was the startup phase, and after that we attained a steady state. So for example, the target temperature was 225. This is the temperature at which we wanted to do torrefaction. Once we attain that, and that's when our actual process or actual laboratory measurements start. So we start with equivalence ratio close to 1 or 1.1, but when we attain the steady state, we can switch to the desired equivalence ratio for our experimental conditions. And if we increase the biomass flux, keeping all other conditions similar, we reduce the startup phase. And at this point, when we attain the target temperature of 225, we should have stopped, like we should have switched to desired ER, and we would have got this trend, like the similar to previous one. So what we see, but we did not stop the experiment, and we let it run, and we attained a higher steady state temperature, but for it depends on the requirement of the experiment. What we can see from here is like if we increase the biomass flux, we can decrease the startup time. But again, I won't comment on this like if we are consuming more biomass in this place or the less biomass in this place. It's difficult to tell because the total time is required less and the mass flux has gone high. So it depends on other factors also. So there was a need to go in more depth about this, and we proposed a conceptual model on this. So what we assumed was like when we burn initially some part of biomass, that's the lowest portion of the reactor is the hottest part, like at say temperature TH. And when flue gases flows through the reactor through the biomass bed, it releases at temperature say TC, at the cold temperature. Then there is the wall of the metal and the insulation, and of course the biomass. So the heat has to flow through all these three resistances. And to analyze like the total thermal inertia of the reactor, we need to know the contribution of each of these components. So as we can see for our lab scale reactor, the smallest one, the contribution from metal was very high. So the most of the heat went in heating of the metal of the reactor. As the reactor scales up, this percentage is bound to change, but still metal was the highest one. So these are the simple energy balance equations which we applied for post-combustion flue gases for the metal. And when we played around this, we got the equation for startup response time scale, which says it was proportional to the dimension of the reactor and inversely proportional to the total thermal resistance factor, which included the resistances of both the metal, insulation, and the biomass. So we had some experimental data, and we got some data from these models for 3 different reactor dimensions. And as we can see, like this was for the thick reactor. As we scale up the reactor, the startup time gradually increases. So the scaling up doesn't have much impact on the startup time. But if we increase the biomass flux, we reduce the startup time by some fraction. But this is interesting. When we reduce the thickness of the metal of the reactor to 1.6 mm, we reduce the startup time significantly by 1/4. The green circle, those are the experimental results, and the other ones are obtained from modeling the those equations. So the reason for this being like metal being the highest contribution in that heat transfer process, and also like as the reactor scales up, this the startup time is like dependent on the thickness of metal to the second order and the thickness of the insulation. So from this we get idea like what kind of metal or what kind of insulation we should use to optimize or increase or decrease this startup time. Now that we know the startup time required for the reactor, it's important to know how much biomass has been consumed. And for that, we defined a factor called as biomass consumption. It's like total biomass consumed during startup by the mass flow rate. And it gives us, in terms of time, like as in this case, we can say that, okay, we consumed the biomass worth of 30 minutes of operation. Had we not consumed that biomass in the startup, we would have added 30 minutes of our steady state operation. So this is a measure to understand like if we have consumed more biomass in startup or less biomass in the startup other than the biomass mass flux. So that was all about startup, and in the shutdown, I will touch upon the quick cooling strategy for shutdown. And that was like, if you want to cool down the reactor quickly, the simple strategy is empty the reactor, get all the solid product out, and let air to pass through the reactor. And it's the forced convective cooling, which will be the fastest mode to bring that reactor to the smallest or the room temperature as soon as possible, like safe enough to leave the reactor at that state. And here, when we characterize the cooling response time, here it was proportional, like inversely proportional to the resistance and the scale of the reactor. So because we talked about like forced convective cooling, so that relation between this reactor cooling time and velocity of air at which it is injected into the inside of reactor after operation is done, it's a sort of inversely proportional. And we can see if we allowed it to cool under natural convection, the temperature drop is like little slower. But if we force it at some velocity, it's much quicker. But again, then there is an optimum beyond which we should not like spend the work on the blower to send more air unnecessarily. Because if we can achieve cooling for 1.9, why do go for 2.8 centimeter per second? So this way we know like how much air we should put in the reactor for cooling to ensure that it cools down quickly. So these were the experimental and modeling results for different sets of reactors for cooling time. Again, it's similar, like as we scale up the reactor, the cooling time doesn't drop like substantially. It's a slight drop in the cooling time. But as we increase the air velocity, like the forced convection, it drops down significantly. But again, if we reduce the thickness of the reactor, we reduce the cooling time as well substantially. So most of the, like to summarize, but before that, let me just point out, most of these results are pretty obvious. Like it's simple, like if we reduce the thickness, if we increase the air, we can get quick start of quick cooling. But still, I think it can be looked upon as a research problem and given like more concrete basis on theoretical explanation, like based on heat and mass transfer models and these kind of transition time scales. And for actual operations where people would have different priorities, they would have to adopt different strategies to start or shut down the reactor. And this kind of conceptual framework would be helpful to understand or to analyze, okay, I should do this or I should do this based on the objective of the user. So we have been doing some more experiments at the lab scale reactor also, and our observations are like much different from what we got at a small scale reactor of higher thickness, because the losses in that are like increasing proportionately as we scale up the reactor. So the crux of the like gist of the matter here was like thermal agility should be reduced for the system, or the thermal inertia, which in this case was through reducing the amount of metal used in the reactor. But again, then there are some other factors which we should not ignore, like mechanical strength of the structure or the reactor as we scale up higher based on the density of biomass that we are going to put into that. So those factors should also be taken into account, and that's what we are doing in our future models. And thank you.
Okay, thank you for that very interesting talk and for moving us a little bit closer to being on time. We have time for a question or two.
Yep.
Yes, please, Buzz.
In this talk at the start, Lee mentioned that the big factor in cellulosic ethanol plants not achieving sort of productivity that we hoped they would was that we hadn't really given enough time to through going on the experience curve. How do you think your work could feed into that, to making plants more efficient?
Okay, I won't talk about the making plant efficiency, but I can definitely talk about making product efficiency. So if we have a biochar, if we don't have a consistent quality of biochar, what's the use? Like it's like in a bag of biochar, if a portion of biochar is like less torrefied and portion is more torrefied, the carbon contents are different, and it would affect the application. So torrefaction is like a pre-treatment process kind of thing. So we carbonize the biochar, and that biochar could be used for further application. So if we have reached a steady state operation, so temperature are fixed, pressure is fixed, residence time is fixed, then whatever we feed in, whatever we get is of consistent quality. So we can rely more on the quality of the product, and we can assure that it's of one quality.
So if I was making biocapacitors to go in electric vehicles, for instance,
Yep.
you want to make sure that they all behave the
Same, yeah, yeah.
And what you present here is a way to kind of ensure that quality.
Yeah.
I got it. Okay.
Yes, please. Charles.
Your temperature about 250.
Yeah.
What is the intended applications for the biochar you produce?
Okay, so one of the applications is like same as you mentioned, soil amendment. So when during our customer discovery trip, like this torrefaction also improves the porosity of the biomass when we torrefy it. And if we mix it with soil, adding some nutrient blends in it, the porosity or the increased retention capacity for nutrients helps in reducing the total amount of fertilizers that is required in the soil. And other thing, it helps to neutralize the acidity of the soil. Yeah, in places like India and Africa, where we are targeting to commercialize this technology, we have several states which have got acidulated soils due to excessive use of commercial fertilizers.
Okay, let's take one more question, please.
Yeah.
Could you say that again?
Okay, thanks. What's the mass yield or energy yield of your torrefaction process using your system?
Okay, so typical, like as reported in literature, mass yield should be around 60 to 80%, and energy yield should be 70 to 90%. In our system, we are at the lowest side, like 70% mass yield and 75% energy yield. But yeah, we can always improve on it by adding like effective insulation and avoiding losses. Yeah.
Okay, thank you.
Thank you.
Let's thank the speaker again.